This is AS and A-level chemistry lecture series and 30th lecture. I'm Hussain, former professor, Department of Chemistry, University of Dhaka, Bangladesh. We have been talking about the reaction mechanism of organic molecules, and that's what we are continuing now. This slide shows the addition reactions of alkenes. Almost all organic molecules do show addition reactions. In this reaction, one of the bond of double bond in carbon-carbon is broken and form a new single bond and thereby form a compound. In general, we can show this. This is a alkene skeleton. If we react with a diatomic molecules or a binary molecule, we'll see that this, if it is XY, that this double bond breaks up and we get X and Y here. If it is Z2, then we double bond breaks up and we get Z and Z. This is a schematic diagram of addition reactions of alkene. Now we are going to addition reactions of alkenes with hydrogen in presence of nickel and platinum catalyst. And if we heat this, we get hydrogenation of this and get from alkene to alkane. And this is what is margarine is manufactured using this reaction. Well, if we take HX, how alkene reacts then? HX is bubbled through a concentrated solution of hydrogen halide, which means hydrogen fluoride or hydrogen chloride, hydrogen bromide, or hydrogen iodide at room temperature. Then we form halogene-alkane compounds. Halogene-alkane compounds. That's what we have also said, discussed in our earlier lecture. There is alkene, and if we take hydrogen bromide, we get bromoethane. With longer asymmetric alkenes, that means this is a simple alkene. If it is an asymmetric alkene, that means let's say it's HCH3 here and then CH2, double bond CH2. This is what's called asymmetric alkenes. If we name this, it's a propene, and there are always two possible products that form. One is, in this case, particular case, one is bromopropane, another is 2-bromopropane. Now, these two possible products, which one will be the major product then? That's what we are showing here with the reaction mechanism. Yeah, that we know the hydrogen bromide is polar molecule, and then here it's a electron density higher here and lower there, and therefore it's a delta plus here and delta minus here. So we get immediately a product like this. And this is a secondary carbocation forms. This is secondary carbocations which forms intermediate, and then finally we get 2-bromopropane. And 2-bromopropane is the major product. Yeah. Well, addition of steam then, what happens then? This reaction is being used in alcohol industry to produce alcohol from steam. What do they do? Gaseous ethane. They take gaseous ethane at high pressure and temperature in presence of some catalyst. In this case, concentrated phosphoric acid catalyst, to form ethanol. But do remember that the ethanol found in drinks is not produced by this process. It's produced by fermentation of glucose. So here is a reaction of ethane in presence of steam and phosphoric acid catalyst, and we get ethanol here. This model is a ball and stick model. Ethane, and then this steam or water, and then concentrated phosphoric acid, and we get this ethanol. Okay, then we go for mechanism of electrophilic addition to alkenes. Oh, what do we mean by this? Double bond in alkene, say that it is ethene. What we do have a sigma bond there and a pi bond there in double bonds. Therefore, we have 4 electrons in this double bond. So, although ethene is a non-polar molecule, but there is a area of high electron density around the carbon-carbon double bond. This is why alkenes are open to attack by electrophiles. What is electrophiles? Electrophiles is an acceptor of a pair of electrons. So hydrogen bromide is a polar molecule. So due to a difference in electronegativity between the hydrogen atom and bromine atom, the hydrogen atom carries a partial positive charge, but bromine atom carries a partial negative charge. That's what we said earlier. And in this mechanism, the addition mechanism, the hydrogen atom acts as an electrophile, accepting a pair of electrons from this and in the alkene, and that's what is shown in earlier slide also. How a bromine can attack them. Bromine is a non-polar molecule. How it attacks bromine molecules and ethene molecules from each other. The area of high density in carbon-carbon double bond, which repels the pair of electron in the bromine single bond, and thereby in nearby bromine atom. This makes nearer bromine atom slightly positive charge. This bromine atom slightly positive charge, and further bromine atom is negatively charged. And that this is a carbocation, and then we form 1,2-dibromoethane. Next slide, we say oxidation of alkenes. What we do by this? How we oxidize alkenes? Yes, we oxidize alkene. We take a oxidizing agent and potassium permanganate, aqueous media, is a powerful oxidizing agent. We take this, and depends on the condition chosen in reaction, what happens in dilute solution of potassium permanganate at room temperature, the purple solution turns colors. This alkene is converted into a diol. This is this oxidation we should die, and this reaction can be used to test for compound having unsaturation. But we also commonly test compound unsaturation for decolorization of bromine water. Well, what happens if we take more concentrated acidified potassium permanganate solution? The harder oxidation condition, the carbon-carbon bond, double bond in alkene is broken completely, and the OH group of the diol formed initially are further oxidized to what? Ketones, aldehydes, carboxylic acid, or carbon dioxide gas. This actual product depends on what sort of bond in the carbon atoms in the carbon-carbon double bond, how it is attached with other two element or atom. Well, we summarize this then, how this reaction, what happens in carbon. If it is, that's just 2 hydrogen atoms attached here, and then in this case we get carbon dioxide as product. If we then see this is not only hydrogen. If we have 1 hydrogen atom and 1 alkyl group, we get first an aldehyde, and then further oxidation we get carboxylic acid. That is what we show here. You see here in carbon 1 hydrogen, and that is 1 alkyl group, and then we get first aldehyde, and then further reaction it gets carboxylic group. If the carbon atom this carbon atom is bonded with 2 alkyl groups, like R1, R2, and then R3, R4, what happens then? We get ketone, yeah. And that is a schematic diagram for this summarization of oxidation of harsh condition to alkene. That's it. We get this, what you said, if it is two hydrogen, we get carbon dioxide. If it's one alkyl and one hydrogen, we get aldehyde, and further oxidation, we get carboxylic acid. And then one alkyl, two alkyl group, and then three alkyl group, four alkyl group. We get then a ketone, it is a ketone. So this is how we see the oxidation of alkene. Now, a very important compound, which we call addition polymerization. It's a very, very important, industrially, one of the most important condition of organic molecules. So, alkene is in the basis of plastic industry, what I say now, molecules of ethenes as well as other unsaturated compounds can react each other under right conditions to form polymer molecules. Okay, a polymer is a single chain, a long chain molecule made out of many repeating units. The small reactive molecules that react together to make the polymer are called monomers. So that is a monomer. That is a monomer. Ethene occurs, the double bond breaks up, and we get single bond. So this is a monomer. The display unit is like this. So I show this reaction by a displayed formula, and it shows like this. This N can be very large, up to 10,000 unit. So this is a repeat unit. Okay, so this polymerization reaction is as follows. I say that, and then you see we can do the same thing with polyethylene and also propene. This is propene, and then this is a reaction unit of unit, reaction unit, and then this is the long chain polymer of polypropylene. So this function. Okay, we go further. This is substituted alkenes. We take a chloroethene. This is a chloroethene. This molecule is chloroethene. Its repeat unit is this, polychloroethene. And there it is the three-dimensional display of PBC, polyvinyl chloride. So this is the repeat unit. This is the repeat unit. You see, two hydrogen with one carbon atom, one bond is there, and then it is one hydrogen with a carbon atom and a chlorine atom. So this is the repeat unit of polyvinyl chloride. If we take the next one, how can you reduce the repeat unit of an addition polymer? So if a monomer of carbon-carbon double bond is given, then simply turn the double bond into a single bond. And in either side, carbon atom has another bond. And that's what is the, so this is the monomer of the addition polymerization, and this is the repeat unit. And that repeat unit will be 10,000 linking together. Okay, we can identify the monomer present in a given section of a polymer. So first what one should split the polymer chain into its repeat unit. So if let's say part of an additional polymer is this. This is aromatic unit. And then if we do it like this, then we get, this is the repeat unit of the polymer. You can see this is the repeat unit. So what is the repeat unit? And then if with this double bond here, it becomes the monomer of this additional polymer. Well, this is a problem for us. Yes, we do know that there are very many uses of polymer, but we also know that the polymer, specifically, let's say polyalkenes, are resistant to chemical attacks. It is very much resistant to water, acid, alkali, and resistant to chemicals. So, as it is very resistant to chemicals, it takes hundreds of years to decompose the dumped landfill sites where we dump the polymer. So they are non-biodegradable. Therefore, it is an environmental issue, this polymer. Okay, one solution could be that we can burn this, but that we see in the combustion of hydrocarbon, that we do get carbon dioxide, toxic gas, very toxic acidic gas, etc. So if we solve this by burning, generate electricity from here, then we can form carbon dioxide. So, and that carbon dioxide is not a solution for combating the global warming. And then we do also get incomplete burning. We do also get toxic carbon monoxide gas, which is very much undesirable compound for environment. And then if we take some polyalkenes with let's say chloroethene polyalkenes, we get acidic hydrochloric acid gas, which is also a very toxic gas for environment. So therefore, we do not go for burn, but a better solution could be if we made the polymers which is biodegradable, and that solution we can call condensation polymers. This polylactic acid, this is biodegradable. Okay, that may compost in months. So rather than tens of years of additional polyphenolates. So here we are showing a few important additional polymers. Ethene, we talked about it. Propene, we talked about it. Chloroethene, we talked about it. And that is the repeat unit of polyethene. It is the repeat unit of polypropene. Is it not? And this is the repeat unit of polychloroethene. What happened? This polyethene, that is what polyethene, light, flexible, easily molded, transparent, good insulator, resistant to water, acid and alkali. That's what I said. And we use this in plastic bags, bottles, bakers, insulation, and other purposes. Well, as I say, it's an environmental issue. We do see also the types of polymers that can be recycled. We know that if we can recycle this polymer, we can get out of this environmental issue. We can address the environmental issue. So the polymer name PET, this is polyethylene terephthalate. We do what is it? Bottles of water and fizzy drinks. We can keep it. That is the symbol of PET. Similarly, this is the symbol of HDPE. This is the symbol of PVC. This is the symbol of LDPE. And this is the symbol of PPP. And this is the symbol of PS. These are all polymers. And then we have, if other polymers, we do symbolize it like this. Why we talk about it? We talk about because we can get the symbols and know what is going on in it, what sort of polymers it is. And this is a repeat unit of PLA, that is polylactic acid. Okay. With this, probably we complete this lecture, and then we take the other organic molecules, chemistry and reactions in our next lecture. Thank you very much.